Why do you need Dedekind cuts? Are they a kind of pie?
Real analysis studies the real numbers under the hypothesis that they form a complete ordered field. To show that this is true, we need to construct the real numbers from something simpler, such as the rational numbers. One way to do this is with Dedekind cuts.
What are Dedekind cuts for?
Now we can define the real numbers to be the set of all Dedekind cuts. The rational numbers come from cuts like the blue one, and the irrational numbers come from cuts like the red one. An ordered field has an ordering and the addition, subtraction, multiplication, and division operations. We need to define all of them for the real numbers. For example, A is less than or equal to B means that the cut A is a subset of the cut B. Now we state the best criterion for Riemann integrability. Let f be a bounded function defined on a closed interval from a to b. F is Riemann integrable if and only if the set of points where f is not continuous has measure 0. Since f is bounded, let the absolute value of f of x be less than or equal to big M. We first prove the reverse direction. Assume d has measure 0. Given epsilon greater than 0, set alpha equals epsilon over 2 bracket b minus a. Because d alpha is a subset of d alpha also has measure 0. Thus, there exists a countable collection of open intervals O sub n, such that d alpha is contained in their union, and their lengths sum to less than epsilon over 4 big M. Now we prove the forward direction. Assume f is Riemann integrable. Fix alpha greater than 0. Let epsilon be greater than 0. There exists a partition p sub epsilon of the closed interval from a to b, such that the upper sum of f with respect to p sub epsilon minus the lower sum of f with respect to p sub epsilon is less than alpha times epsilon. Over the subintervals whose interiors contain points in d alpha, big M sub k minus small m sub k is greater than or equal to alpha. Thus, the upper sum minus the lower sum is greater than or equal to alpha times the sum of delta x sub k. Then the sum of delta x sub k is less than epsilon. In this video, we will prove the bare category theorem. First, we will define metric spaces and completeness of metric spaces. Then we will look at the topology of metric spaces, which is necessary to state and prove the bare category theorem. Finally, we will prove the theorem itself. This means that x sub n is a Cauchy sequence. And since xd is a complete metric space, x sub n converges to a point x in x. For each n in the natural numbers, x sub m is in v sub epsilon sub n plus 1 of x sub n plus 1 for all m greater than or equal to n plus 1. Then x equals x sub m for some m greater than or equal to n plus 1, or every neighborhood of X contains some x of m not equal to X. This means that X is in v sub epsilon sub n plus 1 of x of n plus 1, or X is the limit point of v sub epsilon sub n plus 1 of x of n plus 1. Thus, X is in the closure of v sub epsilon sub n plus 1 of x of n plus 1, which is contained in v sub epsilon sub n of x of n, is contained in O sub n. Hence, X is in the intersection from n equals 1 to infinity of O sub n. Any intersection from n equals 1 to infinity of O sub n is not empty. Let E sub n be a countable collection of nowhere dense sets. For each n in the natural numbers, the complement of the closure of E sub n is dense and open. The union from n equals 1 to infinity of E sub n is contained in the union from n equals 1 to infinity of the closure of E sub n, which is equal to the complement of the intersection from n equals 1 to infinity of the complement of the closure of E sub n by De Morgan's law. Because the intersection from n equals 1 to infinity of the complement of the closure of E sub n is not empty, its complement is not all of X, completing the proof. In this video, we will prove the first isomorphism theorem for groups, sometimes called the fundamental theorem of homomorphisms. It states that if phi maps the group G to the group H is a homomorphism, then the kernel of phi is a normal subgroup of G, and the quotient group G mod kernel of phi is isomorphic to the image of G under phi. It is easy to show that the kernel of phi, that is, the set of G in G, such that phi of G is the identity of H, is a subgroup of G, and that the image of G under phi is a subgroup of H. We will start from the definition of cosets and normal subgroups. Then we will construct quotient groups by defining a binary operation on the cosets of a normal subgroup.